All right, guys, welcome to the second part of the ISEM lecture on sectorial operators and sesquilinear forms. So as I promised you last time, right, I told you there's two things I'm going to introduce more or less separately, namely sectorial operators and some recap on sesquilinear forms. And then in the second lecture, which happens to be today, we're going to put them together and try to see how sesquilinear forms can sort of turn into a generating machine for sectorial operators. All right? So let me quickly recall that in all that's going to follow, and as in the last lecture, there's going to be an ambient Hilbert space H. There's going to be a subset V, which itself is a Hilbert space for possibly different norm. The V is densely included in the H, and A, as always, will be a sesquilinear form on the smaller space V. Okay, and then we're going to start today's lecture in the driest possible way, namely with a definition, but that definition is going to allow us to recapitulate a little bit the vocabulary from last lecture. So this is about the adjoint form. The adjoint form of A is defined, or is denoted by A star, and A star of UV is going to be the same as A VU bar. Is it AVU bar? Is that what I want to do? I guess so. Okay, so what is that good for? First observation is a sesquilinear form can be symmetric, and symmetry of the sesquilinear form precisely means that this adjoint form is the same as the initial form A. Okay, and then we can also relate all the other vocabulary or all the other properties that a form can have by making the following observations. Well, if I calculate the absolute value of the adjoint form at some pair UV, then this is, of course, the same as the original form in absolute value combated at VU, because the complex conjugate doesn't change anything, and also the real part of the associated quadratic form is the same as for the initial form. Okay, and that means two things. If I look at properties, for example, boundedness of A star means a lower bound for the form in terms of upper bound of the form in terms of the V norm of U and V is just the same thing as doing this boundedness of A. Okay, and then so this is boundedness. Upper bound for this guy is the same. Okay, so we can say boundedness is stable under taking adjoints. And then we had all the other properties which implied something on the real part of the quadratic form. Okay, so we have accretivity, which was saying that the quadratic form is bounded in real part from below by 0. And you see from this that this property is stable upon passing from A to A star. Then what else did we have? We had coercivity, which said that the quadratic form in real part is bounded from below not only by 0, but by the square of the V norm. Well, once again, this equality tells you that coercivity is also stable under taking adjoints. And then we had ellipticity, which was more or less the same as coercivity, except that on the left-hand side, we were adding a little or maybe a substantial part of H norm. And once again, the coincidence of the real parts of the two forms tells you that also ellipticity is stable under taking adjoints. Okay. So keep all these things in mind. What we're going to work with most of the time is going to be a bounded, accretive, and elliptic form. So we're going to use all of the things. Okay. So the overall goal for today's lecture is to do this following. So I have a bounded, accretive, and elliptic sesquilinear form on V. And I'm trying to use that form to somehow construct an operator in H. Okay, so there's going to be a construction. And what I want to construct is a sectorial operator in H. Okay, so I'm going to achieve that, and also I try somehow to transfer additional knowledge from the form to the operator. Okay. So it's a little wishy-washy, but that's sort of the idea what I try to do. And so how do we do that? In order to do that, we somehow have to complement this picture that V sits inside H by putting another even larger space on the other side of H, so that the H is squeezed between V and this other space. And this other space is going to be the anti-dual space. Okay. I'm just worrying that the microphone is not behaving as I expect it to be, but probably that's what it is. Okay, so definition. I want to define the anti-dual space. Maybe we're going to divide it into three. So the anti-dual space of V, this is going to be V prime, and V prime is going to be all phi that map V into C. And these functionals you should think of, they should be continuous and they should be antilinear or conjugate linear. Okay? Okay, this is why we call it the anti-dual space, because the functionals are not linear, but they are antilinear. Okay, and when working with the dual space or the anti-dual space, I'm going to use the following notation. So there's going to be a bracket indexed by V prime and V, and this bracket is going to be helpful in our understanding of what's going on, but this is nothing else but applying the functional phi to V. Okay, whenever phi is a functional antilinear on V and V is some element of V. Okay, that's just some notation. Right? Why not? Now, comes a longer remark that somehow tries to elaborate a little bit on the properties of that anti-dual space. So first thing is that you quickly realize that V prime is a Banach space where you use the usual operator norm. So the norm of a functional is just the sup over phi of V, where V runs over all normalized elements of the vector space V. Okay? The most important thing in this remark is that this V prime gives rise to something that one typically calls a Gelfand triple. Okay, so I'm claiming that H sits densely between V and V prime. Okay? And of course, at this point, you should say, stop. I mean, this is not obvious. I'm not done yet. I need to tell you how that works. How is it possible? And how exactly do we interpret the fact that the H sits inside of V prime? So roughly speaking, the idea is that H we're going to identify with its own anti-dual space in view of the Riesz representation theorem. And then this identification is going somehow to be restricted to V to explain this embedding. That's the idea. So let's try to make it precise. So this is explained via the following thing. So if I take an element U in H, then I can associate with it. Okay, so associate with it a functional phi index U that goes from V to C by setting phi U of V to be the inner product of U with the V, but for the H inner product. Okay? And this functional explained in that way that uniquely determines U as an element of H. If the functional would be acting on all of H, this would just be the Riesz representation theorem, but because this functional is continuous on H and V is dense in H, the restriction to V is enough to characterize U as an element of H, and so I can use this thing to say that I can also identify U with this functional, okay? And now I'm claiming that this functional is a functional in V prime. Okay, and so to see that, note that phi U of V in absolute value, if you just apply Cauchy-Schwarz inequality in H, right? And so sometimes wise people say it is just Cauchy-Schwarz that gives you everything. So I apply Cauchy-Schwarz here, and now the only thing I'm doing in addition is the stupid observation that the V embeds into H. Okay, so the V norm controls the H norm, and so I can do like this up to constant, and so therefore it follows that phi U is in V prime, and the V prime norm is controlled by the H norm of U. Two things follow at once, and so therefore this tells you that indeed over here we have defined an embedding, and this embedding is continuous. Okay, sweet. Now let's see how a sesquilinear form, like the generic one we are given, can be a generator of elements in V prime if we in addition assume that the sesquilinear form is bounded. Okay, so let's take A V to V to C. This will always be a sesquilinear form with this letter, and let's suppose that this is bounded. Now, let's take an element U in V, and let's make the following observation. If I take the sesquilinear form and I fix U, so I freeze U, and consider for frozen U the expression as a thing where the V, or the, I want to call it for some reason W, where the W varies, then this thing here, what does it become? What is it? Please. It's an element of the antidual space. Exactly. Okay, so this here is an element in the antidual space. I'm going to show you in a second why. And I want to call that guy script L of U because it is associated to U, and all this is simply because when you compute the absolute value of that thing and you use the boundedness of the sesquilinear form, this tells you precisely that you can estimate by the product of the V norms of the two guys. And so when the U is frozen, this is the norm estimate, the continuity required to say that this functional lives in the anti-dual space. And as always, with these bilinear quantities, it not only gives you that this guy is in the anti-dual space, but the bilinear estimate also gives you a norm estimate for script L of U in V prime, because from here you see that the norm as a functional of this guy is controlled by C times the norm of U in V. Okay, so that the association of U with this functional acting on V is continuous itself. All right. So why is this useful for the things I'm trying to do with you? I can use these observations to define now two operators. Are associated with a bounded sesquilinear form. Okay, and for the time being, this is the key message of the lecture. So one operator you already see above, because I have done precisely that. I have used the sesquilinear form and its boundedness to associate an operator with it. Okay, so this is 2.15 definition. And this is a way of associating a bounded operator. Going from V to V prime. Okay, and the association works as follows. I just copy and paste what is written over there, but as it is the case sometimes in mathematics, I get a little bit of further insight by just renaming objects. Okay, so I want to write it in this way. I want to say U, A of U, W is the bracket of script LU and W, and this is the V prime V bracket, whenever U and W are in V. Okay. Why do I like this perspective? Because somehow it says that the operator L helps us in representing the sesquilinear form via the V prime V bracket. And now I could think of doing other types of operators associated to A in the same way if I use different definitions of brackets. Okay, so let's say that this is the representation via V prime V, and therefore this is the operator, this is the associated operator on V. Okay? It's the associated operator on V, and it represents the sesquilinear form via this V prime V bracket. Okay. What other bracket could I try to use in constructing an analogous thing? What comes to your mind? And what would you do? How many other brackets are on the board? Well, there is the H bracket, right? So I could try to represent also the sesquilinear form using the H bracket, inner product on H. And this is precisely what I'm doing next. So the linear operator L And this linear operator I'm defining as follows. This is the pair of all uv in H cross H with the property that now the sesquilinear form of AUW for all W in V is going to be represented by the H inner product using V and W. Okay? And if you believe me for a second, because I'm going to prove that in a minute anyway, that this is indeed a linear operator, then this will be L of U. And then you see that it's exactly the same structure, except that the non-script L operator represents the sesquilinear form using the H inner product instead of the V prime V duality. Okay, and for all these reasons, here I want to say, in complete analogy, that this is the representation via the H inner product, and I'm going to call that the associated operator in H. Questions so far? I thought for a second that this was a stupid move, but it was not. Okay, so obvious question is, how are these two operators related to each other? And what happens is that, maybe I should erase it here because I haven't told you yet that's a linear operator. For the moment it's just a linear relation. But here I want to say that L is a linear operator in H, and it is a very close relative to the script L, in the sense that this L here in H is the maximal restriction of this guy to an operator in H. Okay? Maximal restriction means this guy maps V, which is a subspace of H, into V prime, which is potentially larger than H. And so if I want to restrict it to an operator in H, I just have to single out all the elements where the L not only maps into V prime, but it maps in the smaller space H. Okay? And this is precisely what's happening here. So I claim that the L is a linear operator in H, and that I know its domain. The domain of L, these are all elements U in V, with the property that LU is again in H, and not just in V prime. And the action is consistent, so if U is in the domain of L, then the two operators do the same thing. Okay, and so these two things together mean that it's the maximal restriction of script L to an operator in H. So that's the relationship. It's as good as it could possibly be. Now, it's somehow in the nature of these things that we're doing here that the proof is more or less a consequence of the definitions. All right, so what does it mean for U and V to be in L? By definition, that means, first of all, U and V is in H cross H, but U has to be in V, otherwise this thing doesn't make sense, right? So it means that U comma V is in V cross H. And then we have this identity over here. Okay, but now I can write that using the formalism over here. So instead of writing A of U W, I can equivalently write script L of U W V prime V, because by definition this is the same thing. And then on the right hand side, I wrote V comma W with the H inner product, but because I know that V is an element of H, this inner product is the same as the action of V on W in the V prime V bracket. Okay? This is just the same thing. And this should be true for all W in V. Okay, but then if you look at that, this precisely means what? It means that U comma V is in V cross H, and script L of U is equal to V. It's just the same thing. It's just by definition all of this. And so if you look at what happens in the first component, you see that the domain of L are precisely the elements in V, such that L of U is in H. You see that the operator acts consistently with this guy. So in particular, the L, initially defined as a linear relation, is a linear operator. Okay, so that's the proof. Now, upshot for the moment is that if I assume that the sesquilinear form is bounded, then I can associate two operators with it. And the one I want to mainly work with is the L, which is going to be an unbounded and under additional assumption sectorial operator in H. Okay, so next, I want to make L sectorial. That's my goal. And in order to do that, what do I need for sectoriality? In particular, I need to prove resolvent estimates. So if I want to prove resolvent estimates, I need to know something about lambda plus L, where lambda is some complex number. And if I want to use forms, then I should better make sure that lambda plus L is also associated with a form. And this is not terribly complicated, right? So if I let lambda a complex number and I look at the sesquilinear form A lambda, which is just A lambda of uv is going to be A of uv plus lambda times the inner product in V. The inner product in H, I want, of course. Okay. Then I claim that this is, again, a nice sesquilinear form, and I can associate operators with it. Well, if I do it in V, then it's going to be lambda plus script L on V, and if I do it in H, then it's going to be lambda plus the Roman L. Okay? That's the statement. Okay. So, what do I have to do in order to make that work? Well, let's check some properties. Okay, so I should say that this is on V and this is in H. Okay, so for the proof, first of all, the A lambda, is it bounded as a sesquilinear form? Someone has objections against the boundedness? So I say A lambda is bounded. I claim I can just check mark this, because this guy is bounded, and here you use Cauchy-Schwarz and then you use the embedding of V into H and you get the boundedness on V. Okay, so that's relatively nice, and then you have to write things out for the associated operators. So A lambda of UV, if I use the definition of the curly operator, then this is this. And as before, for the H inner product, I use the definition of the embedding of H into V prime. And so A lambda becomes this guy, and I can just put the two things together in saying that this is lambda plus curly L of U V prime V. Okay, and so for this calculation, valid for every element U and V in V, you see immediately that the associated operator on V is just lambda plus L. That just comes out immediately. What's the operator that I'm going to associate with this sesquilinear form in H? Well, proposition over here tells me that I have to take the maximal restriction of this guy to an operator in H. But here, multiple of the identity always maps V into itself. So the first summand here automatically maps V into H. So if I want to look at the maximal restriction of this guy to an operator of A in H, this is just the same as taking the maximal restriction of this guy to an operator in H and adding the lambda, which always maps into H. But the maximal restriction of this guy to an operator on H is precisely the L. And so if I want to restrict this guy, it's going to be lambda plus L. And then the proof is complete. It's more vocabulary than math at this point, but it's going to be very powerful very soon. Before I need to clean boards for the first time, let me... there's a question. Yes?
The line proof with a lambda, the second scalar product could be H, right?
This one here? Yeah, it could be H, but it can also be V prime V, because it's the definition of the V prime V product. And I have to make it a V prime V, because otherwise I can't put them together. It was initially an H, but by definition of the embedding of H into V prime, this product is the same as this product. U is in V. And so it's also an H. Why? Where? U should be a function. Well, you see over there, on the very right board, I assume that U is in H, and I associate with it a function. And this is my definition of the embedding, which reinterprets this U as a functional acting on V. And then I identify the two objects. So if I would have not done that, here it would be U and V in the H inner product. It would be the same as phi of U on V in the V prime V product. You seem to be confused. Why is that? So, U associates the function that does precisely the H inner product, which is precisely what stands here. So this is phi of U, if I should make it in color. This thing here, this is phi of U V. Agreed? So by definition of this V prime V bracket, this is phi of U V V prime V. But now I said I skipped the notational nightmare between U and phi of U. I identify the two things. And so instead of phi of U, I'm writing U. And so here, U interpreted as a functional acting on V. This guy becomes the same as this. So thanks for stopping me and asking. So you see, it's mainly vocabulary. It's just a lot of identifications going on to make the things turn into a smooth theory. Okay. Other questions? Yes, please.
The identity, the lambda here, is also understood as the embedding.
Yes, because we think of lambda as mapping V into itself, and so it maps V into V prime after identifying all these objects. Okay. Proposition 219 before the break is the Lax-Milgram lemma. We assume you know it, but we just want to write it down in the language that we're using at the moment. And so in this language, Lax-Milgram says that if A is bounded and coercive, this implies that L is an isomorphism from V onto V prime, and you can compute the norm of the inverse, at least you can bound it from V prime to V. This goes by 1 over C, and C is the constant from coercivity. Okay, so this little c refers to coercivity. All right, so that's the Lax-Milgram lemma in this language. Okay, I think we make a short break here because I need to clean the board. I resume at 2:15, and then we're gonna, I promise you, we're gonna start proving theorems instead of setting up notation. Okay, let's go on. So the guys in Darmstadt have been just taken away their break, partly. If you're sitting in front of the computer watching the video, you can always break as long as you want, so huge advantage. Anyhow, before going into a nice theorem, I want to make one connection between Lax-Milgram's lemma and the notion of ellipticity, because you see, Lax-Milgram is formulated for coercive forms, and I told you that for some reason that you're going to figure out later. I'm not liking coercivity at this moment. I much like ellipticity. Okay, so here's a corollary that states something similar for elliptic forms. Right? So suppose that the sesquilinear form is bounded and elliptic. Remember that there were some constants in the definition of ellipticity. There was the omega, the amount of H norm you could add on the left-hand side, and then there was the kappa appearing in the lower bound by the V norm of the quadratic form on the right-hand side. So suppose we have these two constants, and then the claim is straight and simple. Whenever lambda is a real number, is a complex number, the real part of which is larger or equal to omega, then it follows that lambda plus script L is an isomorphism from V onto V prime, and I can compute or bound the norm of the inverse by 1 over kappa. Okay. And so why is this the case? Well, the operator lambda plus L, we've seen before, is associated with the sesquilinear form A lambda from the previous result, 2.18. Okay? And so if I manage to check that A lambda is coercive, then Lex-Milgram tells me that this guy is an isomorphism. And if I manage to do it coercivity with a lower bound kappa, then this is plainly Lex-Milgram. Okay? So in order to do that, let's compute the real part of A lambda of u comma u to check for coercivity. And now if I want to compute that, there's a first part. I'm using the single notation here. So there's a first part, which is just the quadratic form coming from u, and then there's a certain amount of h norm squared added to it. And the way I want to write it is omega UH squared plus lambda minus omega UH squared. Okay, so this way I just add a lambda amount of H in a H norm to this quantity, the quadratic form of that we call A. And then you see if you look at this part, it's the definition of ellipticity that says that I can control this by kappa times u in v norm squared. And this other quantity, well, this is a positive number. Lambda minus omega in real part is also positive. Okay, so the real part of this guy is positive. So the estimate as it stands is correct, and it proves the coercivity of A lambda. And then Lex-Milgram lemma tells you that the associated operator is an isomorphism with this norm bound. Okay. So now let all the notations sit, and let's prove a beautiful theorem using all the formalism that we introduced. Okay, so it's the most important theorem of today's lecture, and it says the following: if A is bounded, accretive, and elliptic, then the associated operator in H, L, is sectorial of angle pi over 2. Okay? Moreover, you have two additional statements, namely the real part of L of u is always positive whenever u is in the domain of L, and you have some sort of enhanced resolvent estimate, and you're going to see in the proof why I say that what I'm going to write here is going to be enhanced or better version of the resolvent estimate required in sectoriality. Namely, I claim that lambda plus L to the minus 1, this operator is bounded on H, and the norm is controlled by 1 over the real part of lambda whenever the real part of lambda is strictly positive. Okay. So bounded, accretive, and elliptic forms generate sectorial operators of angle pi over 2 in H. Okay, before I get in the proof, let me quickly get rid of this statement, because you see this is just A of u by definition of this operator, and so because the form is accretive, this always holds true. So this is nothing we have to worry about. The important thing is to prove the sectoriality. Okay? So this is where I want to put my focus on. All right. So how do we do that? How do we do that? So, proof. For the moment, let me just work with a complex number, strictly positive real part, and let me see what I can get. Okay? And so suppose also that U is an element in the domain of L. Now, be aware, now I'm trying to do one of the hardest things in analysis, namely I'm trying to bound something from below by trying to remember how to write Cauchy-Schwarz inequality backwards. All right, so let me do this quantity in H and let me multiply it by U in H, and then I do Cauchy-Schwarz backwards. So I turn it into an inner product and I make it even smaller by looking at the real part. So this controls from below lambda plus L U comma U. Okay? And then, it's not really a hard thing, is it? But estimating things from below is always confusing, somehow. I don't know why. If you look at the inner product, when the LU hits the U, then you can use this property A, which is a straightforward consequence of the accretivity of the form, to tell you that this contribution is just larger or equal to 0. So what remains is the other contribution if you want to estimate further, and the other contribution is just the real part of lambda times U in H norm squared. Okay, so this is H inner product. And I should also say here, this is a H inner product, of course. Okay, so if you throw some terms around, you can maybe remove this guy for the amount of a square, and then you can put the real part on the other side. And so what it gives you is something that we call an a priori estimate. All right, so this gives a priori estimate, and the a priori estimate says that U in H norm is less or equal to 1 over the real part of lambda times lambda plus L of U in H norm, and that's true whenever U is in the domain. Right. The reason why I call this an a priori estimate is because if I would know that this operator would be invertible, then I could apply this inequality to an element of the form lambda plus L inverse of something, and then this would turn out into a beautiful resolvent estimate, namely precisely this one. Okay? So the strength of the a priori estimate is now whenever, for whatever reason, and for whatever lambda, I manage to prove that lambda is in the resolvent set, then the a priori estimate always gives me the resolvent estimate that I claim down there. Okay? So this gives me some flexibility because now in proving that something belongs to the resolvent set, I don't have to worry about the precise norm estimates. I just have to prove something. Okay? And so in order to prove that some elements are in the resolvent set, I'm going to make a strong assumption, and temporarily I'm going to work only with numbers lambda, the real part of which is larger or equal to omega. Okay, and I'm going to make a drawing of the complex plane here that we're going to use from time to time. Okay, so what happens here? Well, I could think of lambda sitting here. Now I need some further colors to turn this into a beautiful drawing. So there is this vertical line passing through. Then there's the vertical line on the other side. Okay, and for the moment, I'm working with a lambda that sits somewhere here, so suppose that lambda maybe is here. Okay, maybe it sits precisely on that line, even though that's not necessary. And then minus lambda is sitting somewhere else, namely down there. Okay? Okay. So that's the lambda, and now I first want to prove, my goal is to prove that lambda plus L for this lambda is going to be invertible. Okay, so what can I say? Well, 220 tells me that an omega, of course, refers to the ellipticity constant, as always, because the assumption is that the form is elliptic. Okay, and so 220 tells me that lambda plus L going from V to V prime is an isomorphism. Agreed? And so in particular, it's injective and it's surjective. Now 218 tells me that lambda plus the non-script L is a restriction of this operator. So as a restriction of an injective operator, it is injective. Now, I also claim, and this is a little bit harder to see, that lambda plus L, in virtue of exactly the same result, I can also write down that it's surjective. Okay. And now here, do you all agree? If you say no, that's precisely what I want to hear. So let's present. You said no. This requires some small argument. Okay, but I'm going to squeeze it in there. Why? If I want to prove it's surjective, suppose that I give myself some element V in the Hilbert space. Okay, and V I'm going to interpret as an element of V prime. As an element of V prime, it sits in the range of this operator. So it is okay to introduce U as lambda plus script L inverse of V. Right? This guy is just defined, and this guy is sitting in V. Now, what happens if I apply lambda plus script L to it? Well, lambda plus script L of U is V. But surprise, V is in H, because that's where I picked it. So it means that this U guy is an element of V with a property that if I apply lambda plus L to it, I'm going to get back into H. So this means that U is in the domain of lambda plus L, which is the same thing as the domain of L. And it means that lambda plus L of U is the same thing as this, so it's equal to V. So, you know, the problem just solves itself by writing out what we have. Okay? And so that means that lambda plus L going from the domain of L into H is bijective. There's a question. Yes. The issue is that you have to check. So the suggestion is we know that H is a subset of V prime, so we should know that it's surjective. Well, more or less we know it, except that if we want to prove that this guy is surjective, we have to make sure that the image of the inverse that I defined here gets back into the domain of L and not in the domain of script L. By construction, you just get into the domain of script L, which is V. But by the definition as the maximal restriction, the potential problem just solved itself. So you're right, it implies both at the same time. Okay, so that's nice. So I'm going to use the drawing over there from time to time. So now that we know that lambda plus L is bijective, I can also write down an estimate. Okay, so if I want to use lambda plus L inverse applied to some element V in H, then I can use this a priori estimate. If I call this element U, then it's precisely what I told you. Right? And this gives me 1 over the real part of lambda times lambda plus L applied to U, which is just V. All right? The magic of the a priori estimate. And now that calculation I just did, that works for every element in the Hilbert space. So I can be very generous and crossing out something. So let's kill that. Let's kill that at the expense of writing an operator norm. Okay, and so we have a resolvent bound. The inverse is not only defined as a linear operator by bijectivity, but also it is bounded, and we even have control. Good. That's the key thing. Most of the remainder of the proof is going to be some sort of algebra. But before I do that, let me just quickly remind you that lambda plus L to the minus 1, right? This is the same as the resolvent minus the resolvent of L at position minus lambda. If you factorize by a minus, then it's the resolvent of L at minus lambda. Okay, keep that in mind, because now I'm going to work in the picture. And so what I just did with you is I managed to prove that at this point down here, I have a resolvent estimate. Okay, so at this point, I showed you that the resolvent in operator norm is less than 1 over the real part of lambda. Okay, and now I can move the lambda around on this blue line, and I can also move it to the left. So this sort of resolvent estimate is true all the way down there. If I want to prove sectoriality, then sectoriality of angle pi over 2 means I have to consider sectors that are opening by an angle a little bit larger than pi over 2. So potentially these are sectors like this. Okay? And so you see, I have to worry about no man's land in between the blue line and the imaginary axis. So how do I do that, the no man's land? Well, have a look at this distance, right? This distance, this is precisely the real part of minus lambda. Okay? And now, and by the way, yeah, this should be, if I want to make it into a minus nightmare, then this is this, and this is this, double minus, and the length of the segment is, well, minus lambda is sitting here, has a negative real part, so this length of the segment is minus real part of minus lambda. Doesn't matter with all the minuses, the important thing is that the segment here is as long as 1 over the number that sits in the resolvent estimate. Right? And now you had an exercise. You had an exercise 1.15c that says if I sit in the resolvent set, then by this Neumann series I can always fiddle a ball around that point that remains in the resolvent set. And the radius of that very ball was at least as large as 1 over the norm of this resolvent. In other words, if I sit here, then at least I get into the resolvent set the open ball, the radius of which is precisely this distance to the imaginary axis. So around this point, I'm getting a ball into the resolvent set, which looks like this. So I win this whole thing for my resolvent set. And in particular, I win the whole open segment until here. Agreed? And now this works for every point, so I can just move the lambda around, and I see that the whole left half plane belongs to the resolvent set. Now, I do not have a good resolvent bound at this point, but remember that as soon as I have a resolvent bound, I can get back to the a priori estimate, and I get precisely the resolvent bound that's stated over here. So at this point, we have shown that the full left half plane is in the resolvent set, and that this estimate is valid. And up to minuses, this estimate is precisely the same resolvent estimate as written down there. So this one is also done. Fantastic. Questions? Okay, if there's no further questions, then what do I have to prove? What remains? Am I done with the proof?
The sectorial angle is by...
Yeah, I have proved this thing, but I have not proved sectoriality. Okay? So how do I prove sectoriality? Well, sectoriality of angle pi over 2, he's completely right, is I have to take a sector that is slightly larger than pi over 2. So let's do it like this. And this is epsilon. So the full opening angle is pi over 2 plus epsilon. And now I have to prove a resolvent bound. Well, let's take some number mu sitting here. And then you realize that minus the real part of mu, which is this length over here, this is just the same as I have enough colors to make it another color in this drawing. Just have to find the one that I haven't used so far. Okay, so think of it like this. Then there's a right angle triangle. The real part minus real part of mu is this thing here. And then this is the same as this length, which is the absolute value of mu, times the sine of the enclosed angle here. Call this angle theta. Okay? Right. And then you see theta is between epsilon and pi over 2. So this thing here is larger than mu absolute value times sinus of epsilon. And so it means that the resolvent at mu, resolvent mu L, in operator norm, you already knew that it was controlled by 1 over the real part, but 1 over the real part is controlled by 1 over sine of epsilon times 1 over absolute value, which is the resolvent estimate for sectoriality. In other words, as soon as I'm not sitting in the full left half plane, but I'm just sitting within a sector like this with a slight opening angle larger than pi over 2, then within this sector, real part and absolute value are comparable, and I just did the computation explicitly for you to show you that the comparability constant introduces a 1 over sine of epsilon. But the upshot is really that within a sector, you can compare real part and absolute value up to constants. And so you get the sectoriality, and so the proof is complete. Questions? If not, let me continue down here. Because besides the mere sectoriality, this operator L that we constructed from the sesquilinear form had two additional properties, this and this. So real part of L of u is positive, and you have the resolvent bound with a constant 1 over real part of lambda, an operator which has these properties I'm going to call M accretive. Okay, so an operator L with properties A and B in 221 is called M accretive. Okay. Now, we have shown that L is sectorial. So you can write down all of the conclusions from the last lecture. Okay? And one of the conclusions that you can write down is that the domain of L, this was 2.4, maybe C, domain of L is dense in H. That was one of the most impressive conclusions coming from the resolvent bound within the sector. Okay, so domain of L is always dense in H by abstract theory of sectorial operators, but in this setting of operators generated by bounded accretive and elliptic forms, we can say more. We can also say that the domain of L is not just dense in H, but it is even dense in V. Okay, so this is a proposition. In a situation of 221, the generation theorem for sectorial angle, operators of angle pi over 2, dom of L is dense in V. Okay, and the important thing is in V, not just in H. By construction, the domain always is a subset of V because it was defined as all elements in V such that blah, 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 blah. And now it's even dense. Okay? So how do we prove that? It's not completely intuitive why that should be true. When preparing the lectures, we had to think a little bit how we can cook up an easy proof of that thing. But then keep in mind you work in a Hilbert space, right? So if you have no idea how to construct approximants, just say it and you prove that the orthogonal complement of the thing is 0, and then your space is dense. All right, so that's what we're going to do here. The goal is to show that if I take domain of L and I take the orthogonal complement in V, and this is a trivial. Of course, it cannot be empty, but it's trivial. Okay? If I prove that this is trivial, it means that the domain is dense in V. Okay. So let's take an element in the orthogonal complement of the domain and see what sort of information we can squeeze out to make that element become 0. And it's something to keep in mind. I mean, when you're used to be working in LP spaces, oftentimes, like I do, maybe some of you as well, and it's not the first thing that comes to your mind. If you're used to Hilbert spaces a lot, that's the first thing you try. Prove that the orthogonal complement is trivial, and then your space is dense. Okay, so what can I do? I still have to do something with it. I mean, it's not for free. So let me do like this. Let me introduce a functional on V, and this functional should be given by psi of u at V. It's a little bit like in the identification, but here I really use the V inner product. Okay, and then I want to use Lex Milgram at some point. So I look at this shifted form, A omega, omega referring to ellipticity, and maybe I take the adjoint of this form, and the A omega by ellipticity, this means that this A omega is coercive, and if I take the adjoint, it's still coercive. Before you start running in your head some calculations, I'm not using brackets here because the order of putting omega in a star doesn't matter, because omega is a real number. Okay, so now what can I do? I can use Lex Milgram lemma, and I can represent this functional through the coercive form. So there exists some element W in V, and I'm claiming that the functional, okay, so this is the functional, I use two different colors, then you see where I'm going. I can represent the functional through this form, okay, and writing out this form means it's A of V. Then there has to be a star, and there has to be a W and a V somewhere. So how is it? It's going to be complex. It's just a matter of putting complex conjugates. Okay. Okay. So this form, this is A omega star of WV, and then if I want to write out a star, I have to switch the argument and put a conjugate here. Okay. So this thing here refers to this part. This is the same as A omega star of W, V, and then you see that I probably used Lex Milgram. This is probably my wife telling me that I have to get the kids, but not in the lecture. Okay. So I can represent this functional through this sesquilinear form because it's coercive. And this thing that works for every element in V. Agreed? I just represented this functional through the form. It looks like it's leading nowhere, but it does lead somewhere. Because now suppose that V is in the domain of L. Okay? Then what can I say about this term? If you keep in mind where I take the U from. Well, if V is in the domain of L and U is in the orthogonal complement of the domain of L, then U of V is going to be 0. Okay? Great. But also, if V is in the domain of L, it's also in the domain of L plus omega. And so this sesquilinear form can be represented through the H inner product. And so it's going to be omega plus L V W complex conjugate. Okay? This is yellow and this is red. Just rewriting. Now, this thing holds for all V in the domain of L. Now, let's see how many, and this is a H inner product. How many vectors in H are we cooking up when we evaluate vectors of the form omega plus L applied to V? Well, omega was in the resolvent set of L. Okay? So this thing here, this can be anything, or it runs through all of H. Because every vector in H can be represented as omega plus L applied to something in domain, because omega plus L is invertible. All right? So this W guy has the property that is orthogonal with respect to the H inner product to every single element. So there's only one possibility for this. The W has to be 0. But if the W is 0, and I call this equality star, that you see here, well, if the W is 0, then this is always 0. So it means that UV is 0 for every element in V. And now this can only happen if U itself is 0. Right? So star implies U comma V 0 for all V in V. And so U is going to be 0 itself. And the proof is complete. Please. W is not in the omega. Omega is in the resolvent set because the operator has the complete, from your side, left half plane in the resolvent set. And this is referring to the resolvent at minus omega. Yeah, sorry. Of course. Omega is not in the resolvent set. Omega plus L is invertible, and minus omega, thanks for clarifying, minus omega is in the resolvent set. But this expression can reach every element in H. So in H you get 0 for this W guy, and the W guy represents this pairing, and so the pairing is 0 not just for every element in domain, but for every element in V, and then U is 0. It's a strange proof, but it works. Okay. Now, remember that at the very beginning I told you that somehow I try to transfer knowledge from the sesquilinear form to the operator. Once I know that the sesquilinear form is powerful enough to generate an operator, in a way, and now I'm interested in the relation between symmetry of the form and self-adjointness of the operator. Okay, so suppose A is bounded, elliptic, and accretive. Then I can ask myself, A star is a form with exactly the same properties as I told you at the very beginning of the lecture. And so with A star I can associate an operator in H. And the question is, what is this operator going to be? And if there's any justice, then this operator is going to be L star. Okay? And so if this is true, then in particular it tells you that symmetric bounded elliptic accretive forms generates self-adjoint operators. So therefore this is kind of important to prove. Okay. So for the proof I'm going to let L tilde be the operator associated with A in H. With A star in H, of course. And L is the one associated with A. And now I try to prove something. I have to relate somehow this L tilde with the L star. And as always, one inclusion is easy and the other one is a pain in the ass. So let U in the domain of L tilde. This is the thing that's going to work. And now I'm going to write down something for all V in the domain of L. Okay? All right. For some reason I want to use notation exactly the other way around. So V is in the domain of L tilde and U is in the domain of L. Okay. What can I do? U is in the domain of L, so I can write down L of U, and I can test it against V in H. And then because L is associated with the form A, this is going to be A of UV. Now, A of UV can be expressed in terms of A star by switching the components and doing one more complex conjugation. But then because V is in the domain of L tilde, under the complex conjugation, I can represent this thing as L tilde of V, comma U. And then I flip the order and it gives me U L tilde V. So this means, by definition, that this V guy is in the domain of the adjoint of L. Okay? So this means V is in the domain of L star, and also it means that L star of V is precisely the element that's sitting here. So this is L tilde of V. Definition of the adjoint operator. Okay, so I prove that every element in the domain of L tilde is also in the domain of L star, and that the action of the two operators is consistent. In other words, I've proven to you that L tilde is a restriction of L star. Okay, so I have one inclusion. Now I have to pimp this inclusion to become equality. And so what can I do? Well, there was a sweet exercise that you had on the first lecture, on the first exercise sheet, telling you that if I can manage to prove such an inclusion, and I can make sure that these two operators share one resolvent element, then they have to be equal. Now this guy here is sectorial of angle pi over 2, so minus 1 is in the resolvent set of L tilde. Minus 1 is also in the resolvent set of L by exactly the same result. And because going to the adjoint just means complex conjugation of the spectrum and hence the resolvent set, I can also say that resolvent set of L star also contains minus 1. And because of that, I can take orange chalk and I can make this an equality, and then the proof is complete. Now there is some sort of coincidence in the statement that I proved, because if you take ellipticity and boundedness of the sesquilinear form for granted, then I had accretivity as an assumption, and accretivity means that the values of the quadratic form, they are in the right half plane. Okay? So accretivity means that A of U is always an element of the closed sector of opening angle pi over 2. It's the same thing as saying that the real part is positive. This was accretivity, and then elliptic, bounded, and accretive form gave me an operator that is sectorial of angle, and it was pi over 2. Okay, so the question is it potentially true that this pi over 2 is the same as this, or are these two different pi over 2s? And the answer is going to be these are the same, and you can make a statement that is slightly stronger by considering forms that not only take their value in the closed sector of opening angle pi over 2, but in some smaller sector. Okay, and so we need two definitions to make that work. Okay, so I'm saying that a sesquilinear form A is sectorial of angle pi over 2 if it is true that A of angle phi, and phi is going to be between 0 and pi over 2, if the values of the quadratic form are all trapped in a sector of opening angle phi, and this should be, of course, for all u in V. Okay. So that sectoriality, the limit case pi over 2 would be just accretivity, which we defined before. And if you want, this is the same thing. Okay, it's the same thing as saying that you can bound the imaginary part of the quadratic form by the tangent of phi times the real part. Okay. This is just the trigonometric explanation for being in a sector. You just write it out and you see that's what it is. Okay, and then if you want, there's a third lemma that is useful in order to do anything with it. So if A is bounded and theta is a number between minus pi and pi, then you can look at rotated forms where you just take the sesquilinear form A and you multiply it by complex rotation, and you can associate an operator with it because this is still bounded, and no surprise, rotation of the sesquilinear form just means rotation of the operators. Okay. This you can just prove by basically writing out what that association is, and then it's more or less the same proof as for the shifts of the form that I did earlier on in the lecture. Okay, and so with all these things set up, here is the enhanced version of the generation theorem that I proved in the middle of this lecture, and it is what it should be. So A is bounded, it's going to be elliptic, and it's sectorial of angle phi. Okay, and phi is going to be 0 pi over 2. And then this implies that the associated operator L is sectorial of angle phi. All right. And so it's the deeper explanation between this fact showing that indeed the two versions of pi over 2, they are the same. Okay. It's going to be tough, but I try at least. So what's the main work of that thing? Okay. The main work is what I'm going to show you, and then the details you're going to feed from the lecture notes. Okay, the main work is to show that you have a complex plane, real part and imaginary part, and if the form is accretive, so the quadratic form takes values everywhere here, then you get the resolvent estimate here. Now, if you would know that the quadratic form takes values in a smaller sector, okay? So suppose this is phi, and the sesquilinear form takes values only in this sector, then if I'm sitting outside of this sector, I can try to rotate the whole thing in a way that this point moves to the other side, and in a way that this line dotted under the rotation goes here. Okay? And so instead of proving a resolvent bound for lambda, okay, so I try to prove something like, I want to look at R lambda L here. I'm doing a rotation of that whole thing, and I'm going to look at the rotated lambda with respect to the rotated operator. Okay? And if you say, look at this, this is lambda minus L to the minus 1. If now you rotate by some number, say e to the theta, and you get e to the minus e to the theta lambda minus e to the e theta L to the minus 1, then it's just a normalizing factor missing. If you put this out, it becomes this. Okay? And so bounding the resolvent at this specific lambda is as good as bounding the resolvent at a rotated lambda for the rotated operator. Because this is just a scalar. And if I can prove that this resolvent exists, then also this exists and vice versa. And so the only thing that you have to do in this proof, and it's only the details that are somehow tedious to write out, but modulo these details that you find in the lecture notes, the proof is extremely simple. I take the lambda, I use a rotation by an angle theta to put the rotated lambda over here. Then the rotated lambda is going to be in a new sector, the opening angle of which is outside of her, the opening angle of which is larger than pi over 2. So for the rotated lambda, you are in a sector where every accretive operator gives you the resolvent bound required for sectoriality. And now, if this operator here is sectorial of angle pi over 2, then the rotated lambda will give you a nice resolvent bound with respect to this resolvent, and then you play it back to this resolvent, and the algebra is exactly right that it gives you control of this guy by 1 over lambda, because this guy is controlled by 1 over its absolute value, but 1 over absolute value of this guy is just the same as 1 over absolute value of lambda. Okay, so you do this rotation, you play it back to this guy, and so what you have to check is that the rotated operator is maximal accretive. And how do you do that? Well, you take this lemma down here, you find that the rotated operator is associated with a rotated form. So you have to check that the rotated form is bounded, elliptic, and accretive. Boundedness is a no-brainer. Accretivity as well, if the rotation is such that this thing stays in the right half plane. Ellipticity is not complicated either. You have to write it down. You have to sit down and write out the expression, and then you see it's going to be true. And then you fiddle the details together, and you have to prove. Okay, so I stop here. Thank you very much for listening, joining me. And then next week, Robert is going to take over again, and he's going to tell you about Sobolev spaces and how to use them to define elliptic operators, elliptic differential operators. Okay, so stay tuned and see you around.